To begin with, let us discuss about our wattmeter. The fixed current coil A is in series with the load, and the movable coil, voltage coil V is connected across the load. As you can see from here, right, we have a current entering the coil, and this is the same current entering the load. And we have a voltage, coil which is parallel with the load. It means to say we have the value, we can obtain the value of the current and the voltage, and we know that the power will be equal to the V times I multiplied by the cosine of the phase angle between the current and the voltage. Then this will give us a unit in watts. Okay? Now, there are different ways of measuring a three-phase power. We have a 3-watt meter method. We have a 2-watt meter method. Now, for a special case, if we are measuring a perfectly balanced load, we can use a single one watt meter, and we had to multiply it by 3 to get the P total. Right? Let's go to the next slide. Okay, a single watt meter can also be used to measure the average power of a three-phase system. That is what? That is balanced. So it is limited to a balanced load only. So that the total power is 3 times the reading on that watt meter. Right? Suppose we have a balanced load. Right? We are not connecting this watt meter. We are not connecting this watt meter. We are just using the W1. Then the measurement on W1 will give you, we multiply it by 3, then this will be the P total, the total power of the three-phase load. For what? For only a balanced load. Okay? However, if the load is unbalanced, we can use the 2-watt meter method or a 3 single-phase watt meter, right? This watt meter here are all single-phase and connected to each line, right? And neutral. This O here is neutral. Okay? So let's proceed. The 3-watt meter method is well suited for the power measurement in a 3-phase system where the power factor is constantly changing and the total power average is the algebraic sum of the 3-watt meter method, and this is applicable both for balanced and unbalanced load. Now, regardless whether your load is Y connected or delta connected, we can also use this 3-watt meter method. So in this connection here, we have Y connected or star connection, or we call it also Y connection, right? Y connection, right? So now we have here this portion I1 and E1. It will be our W1, and this will be our W2, and this will be our W3. In our lab volt station, we're going to use I1, E1, I2, E2, I3, E3. When you connect your ammeter, your voltmeter, make sure that let's say for this phase here, you are connecting properly I1 and E2, right? You cannot measure I1 and you're measuring this voltage here using E2. No, the software will confuse. Of course, it will just give you a value, but the software will confuse. We had to follow I1, E1, I2, E2, I3, E3. And we did it already in the previous experiments, Y connected load, right? And here also, we did it already in the delta connected load. As you can see here, the current is being measured, again, the current flowing on the impedance, right? Multiplied by the voltage across this impedance. What is this E1? E1 is also the voltage across here, across this terminal, right? Between A and B. E1 will measure the voltage of BAB. Okay, of course, if we draw the phasor diagram, it will be angle 0, right? E2 will measure the voltage BBC. These are line-to-line voltage with an angle of negative 120 in the case of delta connected load, right? And E3 similarly will give me a voltage BCA with an angle of negative 240, right? And you already know the difference here. Here for delta connected load, this is the line-to-line voltage directly connected across the load, right? And for Y connected load, we have the line-to-line voltage here, and the voltage across the load is the line to neutral voltage. Okay? So this is for the delta. Okay? And then you just add all P total, as I've said, P total here will be equal to the wattmeter reading in W1 plus W2 plus W3. This will give you the total power. Okay, let us go now to a 2 wattmeter method. So can you imagine we are using here 3 wattmeter and now we want to use 2 wattmeter only and still it should show the same total power. How does it happen? And I'm going to show you in detail. Now, I am using here a 2 wattmeter method regardless whether it is Y or delta, this load. Regardless with this Y or delta, what we need is only a 3 wire, the line to line wire A, line A, line B, line C. We don't need to connect the neutral. So here is the connection. We are using wattmeter 1, where line A, we had to connect the current coil, and between A and B, we had to connect the voltage coil. And for our wattmeter 2, we are going to connect the coil, current coil in the line C, and the voltage coil between C and B. So B is just like acting as the common terminal for the wattmeters. I cannot call it neutral because this is still not neutral. It is line B. It is the common point for the wattmeter. Now, although the individual wattmeters no longer read the power taken by any particular phase, still the algebraic sum of the 2 wattmeter in this connection is equal to the total average power also by the load, regardless whether it is Y or it is delta connected. The real power is equal to the algebraic sum of the 2 wattmeter readings. So how can we prove that when we add W1 and W2, the total power will also be the same? Let's go to the next slide. Okay, so we all know from previous discussion that let's say we have a let's just assume that the load that we have is a resistive load and with an inductive load, right? So now this is the phasor diagram of this circuit. We have BAN. So this is our A, this is our neutral here, and BAN angle. So let's write BAN is equal to the B phase angle 0, and BBN is equal to the B phase angle minus 120 from this figure, and CN is equal to B phase with an angle of negative 240 degrees, right? And of course, you know also the BBC is an angle with an angle 90 degrees from this figure, okay? And here, BCA, it will be what? It will be what? So if this is 90 plus 120 here, right? It will be 210, right? 210. 210 plus another from here 120. So it will be 330 from here to here. This is 330 if minus 330, or we can simply say this 30 degrees with respect to this measure. Now, observe P1. P1 is BAB multiplied by IA. BAB multiplied by IA. Cosine theta plus 30. So, BAB multiplied by IA. So, where is IA? We have a resistive load and inductive load from this impedance. It means to say we have a lagging current, right? So, because this is a resistive and inductive, we have a lagging current. So, we can say, we can assume that this is our IA, right? IA with an angle theta with respect to BAN. Right? So, with this case, BAB multiplied by IA, cosine, the phase angle between them is 30 plus theta. 30 plus theta. So, okay, since here is BAB here is B line and IA is also B line, we can simplify this equation as BL cosine theta plus 30. Okay? Now, let us go to our wattmeter 2. Wattmeter 2 is the voltage BCB, voltage coil BCB. So, we have BCB multiplied by IC, which is also a line current. And what is the phase angle between them? Phase angle between these two is if you have this BBC, right? So, of course, we will have this, the BCB is on the other side. Let me just draw it. This is our BCB, okay? And if here we projected that BAN, IA is lagging by an angle of theta, this is also our BCN. So, we can put our theta here. The IC should be on this line. So, IC with an angle of theta, which is also lagging BCN, right? It is lagging BCN. So, now, what is now the phase angle between BCB and IC? So, we can expand this. So, we will have BCB has an angle of is equal to BL, right? With an angle of what? 90 degrees, right? 90 degrees. And we have IC is equal to IL with an angle of what? 120 minus theta. Right? Okay, let us now expand this equation. So, P2 is equal to, we can write BL, IL, right? Then cosine of, what is BBC here? 90. Cosine 90, right? Minus what? The phase angle of this IC is 120 minus theta. 120 minus theta. Right? And simplify this portion. We will have BL, IL, cosine what? Minus 30 plus theta. So, we can rewrite this as P2 is equal to BL, IL, cosine theta minus 30, right? Which is now equivalent to this one. So, let us add together. So, what did we say? We say P1 plus P2 will give us P total, right? So, let's go to the next slide. Okay, we know that cosine from trigonometry, cosine A plus B is equal to cosine A cosine B and minus sine A sine B. Okay? And cosine A minus cosine B is equal to cosine A cosine B plus sine A sine B. So, we will substitute, similarly, we will substitute this in our equation. We can say that if we add P1 plus P2, this is P1. Okay? We factor out BL, right? This is for P2, this angle here. So, cosine theta plus 30 is equal to cosine theta, cosine 30, minus sine theta, sine 30, following this trigonometric identities. Plus, the other side, we have cosine theta